So the basic, going to apologize in advance for a couple of things. One is the brevity and the kind of oblivion is a Navy term for 5 pounds of shit in a 1 pound bag. And so we have a lot more information that we'd like to talk to you about, but we haven't ever been able to fit it into an hour. And so we're going to try to give you the gist of some of the things that we're doing. But this website, vpri.org, and maybe our talks are kind of a commercial to just have you look at some of the stuff there. So I'm just going to spend a few minutes giving you the context for a project that the NSF reviewers termed the preposterous proposal when they turned it down. Anybody ever been turned down by an NSF peer review? Now it turns out that the program managers at NSF have always had the power to override those. And in this case, the program manager did override it, so we got our money anyway. But they only gave us money to cover about half the expenses of this project, so we raised a matching amount of money to do it. And it's a project that a number of us had been thinking about for as long as 30 years, that it would be really interesting to do. And it would be very much in the original spirit of what computer science was supposed to be, as articulated in the 60s by Al Perlis. So, and it kind of starts with the quintessential Maxwell's Equations t-shirt. And this is one that everybody's seen. And if you're familiar with Maxwell, you know that he actually wrote 5 papers arriving at these conclusions in 5 different ways. He did this over a period of years using different models. And the original form of Maxwell's Equations was not fittable on a t-shirt. So this form was actually made by several people, including the Germans, who were much more interested in it than the British, in no small part because Maxwell's equations violated Newton, and Newton was a god. Maxwell was only their best guy in the 19th century, but Newton was a god. And of course, the interesting thing about getting him in this form is, although Faraday's experiments showed that there should be a symmetric relationship between the electric and magnetic fields, the equation didn't show those relations as symmetric, and this asymmetry in this way of looking at things led to Einstein's theory of relativity, and in fact a much simpler form of writing these guys down. And the reason I'm putting it up there is I had a similar experience when I was in graduate school trying to understand programming languages, and I looked at the bottom of page 13 of the Lisp 1.5 manual, and here was McCarthy's formulation of Lisp using itself as a meta-language. And how many people have had the experience of going through this? It takes a couple of hours on a Sunday afternoon to do, and you run out of fingers because you have your fingers down in all the places it recurses and re-enters and so forth. And I felt I understood it when I found the bug in this code. There is one bug. But the thing I got out of it is, boy, after those 2 hours, I understood what programming languages were about a factor of 100 better than I did before I went in. Because McCarthy had carved away all the bullshit and gotten at something that was more powerful than any other programming language of the day, and more powerful expressively than most programming languages today, and had done it in this interesting form. And in fact, it had a lot of effect on subsequent things that were done. And because I had a math degree, I just loved this stuff. And so we tried these ideas a number of times on various projects, including some of the stuff we did at Xerox PARC. That, gee, you can do a programming language in 100,000 lines of code, or you might be able to do it in a page. And there are advantages to the page for sure. So the thing we were speculating about is, gee, it would be really interesting if you could apply this way of looking at processes to an entire system that's well understood, like personal computing. So we have now this interesting idea that if science is the study of and modeling of phenomena in order to understand it better, we actually build artifacts that exhibit interesting phenomena. And what John did is to take the phenomena exhibited by programming languages of the day and find an abstraction that captured them. His abstraction happened to be more powerful than the ones he was looking at, which is kind of an old mathematician's trick. Solve the more general problem if you can. And so the idea here was be interesting to take this body of behavior from the end user to the metal of the machine and try to understand it by making a model that you could actually run that would generate the same phenomena. And so how many t-shirts would it take to do all of personal computing? That's the question here. You can see why they called it preposterous. Because Microsoft's version of this is a few 100 million lines of code. Their operating system and just say Microsoft Office is about 220 million lines of code. But if you think about it with the view of, well, what is it doing really? And how many things in it that Microsoft decided to do differently, for example, are actually the same thing masquerading under a few simple parameterizations. And also, the first time around that this stuff was done, it was only 10,000 lines of code at Xerox PARC, and there's not a lot more functionality now than there was back then. So the idea is this could be a lot smaller. And it'd be very interesting to see, for the same reasons that these two guys are interesting, what this would be look like. So that's what our project is, and there's one more T involved here, which is one of the things that's nice about making things small and simple is you get something like a Model T Ford, which any 12-year-old could take apart in the barn over the weekend and put together. It only had about 350 major parts in it and about 1,000 screws and nuts and bolts and stuff. So anybody who grew up on a farm like I did, where there were still Model T trucks in the 40, they would be routinely taken apart. The reason they were still around is you couldn't really kill them because everything that broke on them was fixable in the blacksmithing shop that every farm had back then. There's nothing. They didn't even have a distributor. They didn't even have gears. They had belts and pulleys on them. But they were real automobiles. So they had this interesting thing. They caused, even though there were automobiles around before them, they caused the automobile revolution in America because they were so easy to manufacture and they lasted well and so forth. So just one Model T story. The gap, the spark gap on a Model T was optimized to be the width of a dime. And somebody asked Henry Ford once, why did you do that? And he said, well, people always lose gauges, but they usually have a dime on them. So he's fully expected anybody who's had one of these things would be able to just fix it and tweak it up. And that's what happened. So it's a nice metaphor. So my theory is, before you write the Ferrari code, you should write Model T code, because there's a 12-year-old kid who just isn't going to be able to understand the Ferrari code, and you have a moral obligation to write that Model T code that is understandable. So kind of the standard model for personal computing is from the the Xerox PARC experience, and so the screen that can display anything, and a way of organizing views on the display. And people have been confused by the difference between desktop publishing, and Microsoft, for instance, has been, and window display. They're actually the same thing. Just these guys have boundaries around the views, and in desktop publishing you don't have boundaries around the views. But aside from that, everything else is exactly the same, and it was done with the same code. So this is a modern version of it. And I'm disappointed in this display because Dan Amelang has done a lot of work to do really fantastic graphics, which some of the things are shown here, and you can't see how crisp and beautiful it is. But this is kind of a modern version of it, done with some of the stuff that we've done. And just to show you a little slant of it here, so I can edit this as I'm used to doing. This thing is programmed completely differently than the way you might think. So for instance, the code behind these paragraphs is the justification, and the editor for it come to about 23 lines of code in one of the languages we developed to do this. And I'm not going to explain exactly how we did this, but I'll just give you a little flavor of what's actually going on here. So you can think of this as swarm programming. So what we have is thousands and thousands of parallel processes running at the same time. And these are all objects. And so the simplest way you can think of doing the problem here is, well, just follow the guy in front of you. If you don't have anybody in front of you, you know where to go. If you're over the margin, tell the guy in front of you. And if somebody tells you they're on the margin and you're the first, there's a blank in front of you, then go to the next line. Right? So that's 4 things that do a text justifier if you have parallel processes. There's no loops or anything. They're just all running, and they're related to each other. So we call this particles and fields type programming, and there's a lot of it in this system. And you notice that I've embedded a view of the entire document recursively into it. So that was operating at the same time. So this is basically this kind of stuff in which each part of the thing has been mathematized and done in a separate programming language. And of course we have to make the programming languages to do it, and we have to make the tools to make the programming languages to do it. But what we don't try to do, so these are the 3 main operating systems. I won't tell you which one the lemon is, but they're all big. And we want to avoid apples and oranges comparison. So the stuff that we're doing is not, there's nothing that we can do that can be honestly compared to what Microsoft or Apple do, because they have legacy problems we don't have. There's a million things. So we don't even worry about that. But here's a t-shirt with a mustard seed on it, and that gives you kind of what we're out after. We're out after more than a factor of 1,000 change in the size of the code that it takes to make this kind of phenomena. Something more like a factor of 10,000. And so if you have the end user at one end and you have a power supply at the other, you have a lot of different kinds of phenomena in there. And the question is, how many t-shirts do you actually have to do? So you can think of the 2.5D anti-alias graphics as you'd love to have that in 1 or 2 t-shirts. So that's regularly a couple 100,000 lines of code. And if you think of the number of different languages you might want to invent to mathematize the different parts of these things. There's probably 5 or 10 different languages you have to do. So you have to have a meta language. Meta language has to deal with itself and so forth. And you'd like to improve semantics of programming and so forth. So we have a dozen or so powerful principles. Here are 10 of them. There's nothing more boring than somebody enumerating a list on a slide. So I'll just point out that most of these powerful principles are ones that have been around since I started in computing in the early 60s. And most of them are not in general use today or in use the way they were originally used. So some of these are things that have been resurrected. So the particles in field is something that hasn't been used very much, but the notion of simulating time, not letting the CPU determine what time is all about, goes back to both Simula and John McCarthy's situation calculus. These are old ideas, but they have the great advantage that you don't get deadlocks from trying to use monitors and semaphores. So the basic idea is if you simulate the time that you're running in, you cannot have race conditions that you haven't explicitly allowed, and so on. So the underlying idea here is that math wins. Not standard math, but math that you actually invent in order to characterize all the different behaviors that you want to have. And with that, I'm going to turn it over to Dan Amelang, who will talk to you a little bit about how we do the graphics, because this is kind of a classic case study of give you this. Dan is a graduate student at UC San Diego and just got his master's for part of this and is on his way to getting his PhD for the rest of it. And what we'd like to do here is to, I don't think anything I said needs questions except maybe to the end, but it'd be great. I brought the 3 people who did a lot of work in this system along. And by the time you get to my age, you're just a figurehead. So I'm thrilled to actually bring people who are doing stuff here and to have them tell you a little bit about how they're approaching these problems, and hope you do ask questions.
Hello. So, like Alan said, my name is Dan Amelang. I'm a grad student like you guys, so go easy on me. I'm getting towards the end of my time as a PhD student, so I'm going to present to you basically where I am on my dissertation work. I have still about a year and a little more than that to go, although I've noticed that kind of just extends forward. It's a tradition of PhD students. Right, so I'm a UCSD PhD student, but I'm also an employee of Viewpoints Research Institute. And so my little niche in this project is the 2D rendering system, because we like to build basically a whole software stack. And we're not allowed to just delegate to the operating system routines. We want to reinvent programming at every level. So I have some background in computer graphics and some in programming languages and computer architecture. And so basically it fell on me to figure out how to do 2D rendering. So the sub-project of mine is called Gezira. And like I said, it's a 2D graphics render in the spirit of this project. The idea is to provide something that's practical, useful for the other projects, sub-projects at Viewpoints to actually use. Specifically, the focus right now is building user interfaces. And so my job is to discover what are the minimal algorithms, the powerful abstractions, new representations, so that I don't use up our code budget just in my sub-project. Because the goal here is, again, is to have engineer the whole system so the whole thing is minimal. So, and again, this isn't really, even though I'm doing computer graphics, the focus here is more software engineering. I'm not going to do anything that's really advancing the state of the art in computer graphics so much. So what are the requirements of this graphics library? Well, today in today's systems, you expect anti-aliased vector graphics. What people use nowadays is typically Flash, SVG, Core Graphics on Mac OS X, Windows Presentation Foundation. So that's kind of not my competitors, but what's similar to what currently provides that functionality today in commercial systems. Right. So in the 2D render, you want to have Bezier outlines for your shapes. You want to be able to display text, transformations, clipping, all pretty traditional stuff. The blending operations, digital images, pen stroking for the outline of shapes. So as I was working on this, I started with the Cairo open source render project, which I'd been working on before I joined Viewpoint, and so I was able to take kind of the lessons learned from working on Cairo, which is the render behind Firefox and various open source applications. And so as I was kind of going through the Cairo code and thinking, stepping back for a bit and figuring out what really is the high-level intention of these coders, I came across the rasterization stage, which is probably the most complex part of the whole software library. Anyone who's taken an undergrad computer graphics course that's had to implement like scanline fill knows that it's kind of tricky getting all the edge cases, and there really isn't a strict formula that tells you what the output should be. It's usually described as some sort of an algorithm with data structures, active edge lists, etc. And so I couldn't figure out, what really is the highest level semantics of rasterization. So, and it's difficult. So I looked at some kind of non-traditional algorithms for doing rasterization, especially things specific to 2D, because I can kind of ignore the complexities of 3D here. And one method kind of stuck out at me. There's this approach called analytic area-based anti-aliasing rasterization that looks sort of like a formula, but everyone's still expressed in terms of like a big case statement. And so I felt, there's still something to be extracted here. So I called my mom. Luckily, she's a high school geometry teacher and a great partner to have in trying to figure out all this computational geometry that I was in the middle. And so we sat down for about 10 days and did like pair programming with pencil and paper. And we did end up with an interesting formula. If you pose a problem this way, if we say, given the XY coordinates of the lower left corner of a pixel, we can say that the coverage contribution of one edge of that shape is calculated this way. So if we just look at it one edge at a time, you can actually, using an approximation square for the pixel, you can, the bottom function is kind of what you want to look at most. It's just, you can actually combine these three pretty much standard functions in 2D geometry in an interesting way that gets you a nice coverage result from 0 to 100. So if the pixel is entirely outside of the figure, it's 0. If it's entirely within, you get 100. If it's on the edge, you get somewhere between the two. I only have 10 minutes, but basically the top one is a variation of the area of a trapezoid. The second one is the clamp function in mathematics, and the third one is a variation of the point slope formula for a line. Anyway, so once we have it for that one edge, then it works out such that the total coverage contribution of the entire polygon is just a linear combination of those edge contributions with a little additional adjustment. So now we have a formula. But this doesn't execute. So I haven't really won yet. But at least I've, posed it in a way that then I can imagine some sort of higher level language that can turn this into executable code. So the punchline is, so then to verify it, I wrote some prototypes. I have this snow demo I'll do for you. Basically, you're going to see 1,000 snowflakes. They're all identical, so it's not very realistic. That all have independent position and a vertical velocity and angular velocity. And I'll just animate them. And I'm not using the GPU at all here. This is just on the CPU. I render it to an image, a bitmap, and then just hand it to the operating system to throw up on the screen. And so this isn't really a speed demon per se, but it's just to prove that, first of all, the visual results are good, and that it's fast enough that I'm not painting myself into a corner. Yeah, and then so after it starts up, it'll fade in a bit. This is actually supposed to be white or light blue on black. You can just imagine this. I'm sorry. It's kind of painful for me. And so I chose snowflakes because we want to render text really quickly without having to use some sort of caching scheme, because that kind of muddies up your code. So as long as I can render something that's text-like, because each one of these snowflakes is composed of 64 cubic Beziers, which is usually much more than what a typical glyph is that you render on the screen. So as long as I can do these snowflakes quickly, then I can make a case that it'll scale out to text rendering. So zooming in just to show you that it's vector graphics, not just raster graphics. It's being scaled. It's coming from the vector primitives at each frame. Yeah, this is like one of those screensavers you can stare at all day, but I hypnotized you enough. So then, yeah, here's the punchline. The goal was to figure out how to express all that in 80 lines of code. And I'll explain what this is. So this is a new programming language called Nile. Again, the goal is to express the 2D rendering in a way that is succinct, can be automatically translated to a variety of execution environments, and doesn't preclude efficient execution. So after writing these prototypes, it seemed to me that the best model for the software would be a data flow stream processing model, more generic than like the stream languages today are kind of more tied to specific to GPU hardware. This is kind of a more abstract stream processing model. So yeah, the idea is that everything is just data streams that are being processed by a series of kernels that have been connected in a network in an interesting fashion, and you get your pixel values at the end of the pipeline. And then we want to optimize the syntax for each one of those kernels for expressing arithmetic, vector computations, basically a domain-specific language for arithmetic stream processing. And then we want to be able to then generate code for a variety of environments. So we'd like to generate code to C because that'll get us sufficient execution. JavaScript is interesting because it's dynamic. We can do demos in the browser easily. It could perhaps, we can make a nice IDE out of it perhaps. We can target more exotic languages like Haskell, which ends up having Nile has very similar semantics to Haskell. And then, we could go blue sky and say, maybe we can generate code that runs on the GPU directly from the math. And maybe we can go even further and generate hardware directly from the specifications that's expressed in this high-level math. We'll see. Haven't done that yet. Yes? Sure.
One of your goals is to make a code as compact as possible.
Mm-hmm.
I can understand why DSL helps with it.
Mm-hmm.
But if DSL also has come with a compiler, if you don't want to interpret it, compiler can be quite good. That's the next part of the story. Okay.
Right. So I am depending on some magic technology that can express my compiler in some very succinct way. Luckily, I'm not the only one on this project. So you can probably tell it comes after my talk. Right, so I'm going to breeze through this real quick, but this is basically an explanation of the semantics of the language with 2 example kernels on the bottom. Yeah, it's kind of a mix of Haskell and APL, but a very restricted subset of Haskell. Sorry, I gotta move on. So now that I have this programming language to express it in, now I can get, the core, more than just the core of a 2D render in about 386 lines of code. Really the first 2 files are the ones that are needed for for the snow demo. The rest of them are kind of, they expand beyond just the core what you need from a 2D render. The compositor does all the compositing blending modes you get in Flash and PDF. Pen stroking gets you the outlines, etc., etc. But now I have to get it to run, even though I have this language. So initially I was just kind of manually translated. I had like two windows open, one with my Nile ideal code, and then one with like JavaScript or C, and I kind of pretend like I were like a compiler during the early stages of the project. But then Alex is going to demonstrate a translator that he worked on that allowed us to generate JavaScript that could allow this rendering code to run in a web browser. So let's see. I thought this. Oh, of course not. Sorry, one. So we can do just basic rendering. And again, the way I do this in the web browser, I'm actually doing all the work in JavaScript. And then there's an API call I can use in the web browser. If anyone knows about the canvas tag, I can fill this a JavaScript array with color values and then tell the browser to just throw those color values on the screen exactly the way I've populated them in the array, which gets me sort of like a rudimentary frame buffer. So you can zoom in and see that, you know, it's anti-aliased. I know it looks horrible on this projector, but it is. So that gets us basic anti-aliased rendering, and then I'll just do one more. Let's see, and then we get a little fancier with Safari has an unusual bug. Sometimes it doesn't pull in. There we go. We can use one of those compositing operations to get the same star that's been rendered but textured with the radial gradient onto the picture background. So you can get a pretty good idea. The color fades away as you get away from the radius. It's kind of a standard 2D rendering. Okay. All right. So, but now we're working on a Nile to C translator. Again, we're doing the manual translation first. Alex is working on translator to go to C, and then hopefully, you know, this is something we're hoping to have in the next couple days. We'll have a practical, real-world graphics render synthesized from this high-level mathematics. And just to give you an idea of how this fits into the whole software development cycle, just for the C generator, we have these Nile files, Nile programs, go through a Nile to C translator. We spit out a header file, a C file, send that through the C compiler. We get an object file, which we link with a bit of runtime support, very little, plus the app, and then you have your application. All right, so everything we have, just general policy in the company is everything is open source, MIT license. You can check out my stuff on GitHub. And the future work is to expand the backends for the compiler, expand the feature set. I want to have something that's pretty close to the commercial 2D renders. And then I'd like to try other problem domains that I'm hoping are well suited, or that my language is well suited for, like audio decoding or 3D rendering, video decoding, data decompression, that type of stuff. So I don't have much time. I'm out of time, so maybe we can hold questions for when we're all done. Does that sound good? Okay.
Thanks, Dan. Is this microphone working? I guess. Hi. So I'm Alex, and just jump right in, I guess. Even before I started working with Alan, I was a programming languages geek, kind of, and I always liked having ideas about things that could help out programmers and stuff. One thing that really gets to me, well, especially at that time, that really got to me, was that you can't just keep having ideas and just sort of, experiment with the ideas quickly, because you have to prototype a programming language when you have these ideas, and that usually takes a lot of time. There's a lot of effort that goes into it. And programming language designers like me, we tend to get lethargic, and feel like, oh man, okay, I have a couple of ideas that might work, but I really have to be selective because I don't have infinite time to implement all these things. And so, I was so upset about this. So I called my mom, and she said, Alex, I'm a dermatologist. What do you want me to do? So that didn't help very much. But yeah, thank you, Alan. So, but luckily, Alan pointed me to some papers from the 1960s and 70s that were really interesting. And one of them was a paper by Val Shorey, who was a guy at UCLA in the 60s. And it was about a language called Meta 2 that he developed. And it was a language, it was a compiler generator kind of thing. It was very similar to parsing expression grammars that are sort of in vogue now. And but this was in the 60s, and the computing resources that Val Shorey had were very limited. And so and yet somehow he was able to come up with this little language that was fairly easy to learn, and allowed him to implement a pretty interesting subset of ALGOL in like a page of code, and the language itself, the meta language, could be compiled by itself in about a page of code as well. And so I looked at that stuff and I thought, wow, I have to implement this on my own to try this out. The bootstrapping was beautiful and everything. So once I did that, which only took a day or so, I felt really empowered because I had been using these larger frameworks like Polyglot for extending Java. And I had written things by hand quite a few times to know that, it was very costly. And so when I started doing this thing with Meta 2, I got excited and I started extending it to kind of catch up with the times. Because, for instance, the original thing didn't support backtracking because resources were limited. And by now, you can do as much backtracking as you want, and it's not a big deal. So anyway, I had some ideas about extensions that I could have on this thing. And this was kind of the birth of my language called Ometa, which we have used to implement several programming languages in this project that we're experimenting with. And the goal of this thing is to minimize the amount of time that it takes to go from idea to a working prototype. And I'm not so worried about the efficiency of the prototype or whatever, as long as I can get something that runs efficiently enough for me to try out the idea and make sure that it's an interesting thing to pursue further and so on. But we've had pretty good luck with that kind of thing, and things that we've made with it have been fairly efficient so far. So what you're looking at right now is kind of like a Smalltalk workspace interface that lets you type in some code and evaluate it on the fly. And this is running inside the browser. I have several Ometa implementations. This particular one uses JavaScript as the target language, as the assembly language underneath. And so in this web browser, I can just type in a bunch of code, like, even any JavaScript expression like that I can evaluate on the fly. But that's not very interesting, right? Because as a language guy, I want control over the language that I'm using. And so the stuff that you tell it to evaluate is not necessarily the stuff that gets evaluated. There's a level of there's an indirection here in this function, called translate code, that gets called with the string that you want to evaluate, and is supposed to return the thing that you pass to the eval function in JavaScript. So it doesn't matter what it says right now, but the cool thing about this is it lets you replace the programming language that's being used in this interface very easily. And of course, it's very self-serving because Ometa is sort of the ideal language, as far as I'm concerned, to write something like translate code. I'm very modest today, I guess. So, let's see here. I don't know why I can't see. Wow, it's fairly big. Oh, I know what's going on. Hang on one second. Technical difficulties. Okay. So, instead of going over the language and stuff, I'm just going to say a few words about it, and then I'm going to show you a bunch of examples and end up with Dan's Nile translator. So, the main idea in the language is that pattern matching is good for most things that you care about in writing a translator. For instance, if all you care about is lexical analysis, you could pattern match on a stream of characters and produce a stream of tokens. Similarly, to write a parser, you can pattern match on a stream of tokens to produce parse trees. And then code generation, at least naive code generation, can be done by pattern matching on a parse tree to output some code, and so on. Even transformations on parse trees and optimizations can be done in the same way. And so, let's start off with something fairly standard. So, a little while ago, I sat down with a friend of mine and I wrote a library in JavaScript that's about 70 lines of code, that implements the semantics of Prolog, including, unification, backtracking, all that stuff. And that's, what's being loaded on the top of the page. The thing that you see right here is a grammar written in Ometa that teaches the browser how to understand Prolog syntax. It doesn't include things like the special list syntax in Prolog, but that doesn't matter anyway because it's just syntactic sugar. So the important stuff is there, and it's fairly easy to grasp and gist and so on. So I'm gonna load this stuff. And okay. Now, down here, I can tell my Prolog translator to answer certain Prolog queries given a few facts and rules, just like you would do in a real Prolog interpreter. And so, in this first example, I'm asking for all the natural numbers, given that 0 is a natural number and the successor of x is a natural number, if x is a natural number. And so, if I select this stuff and tell it to execute, it's saying that 0 is a natural number. Sorry, it's kind of small. 1 is a natural number. 2 is a natural number, and so on. It'll go on forever until I tell it I'm done. And then this next example should be very familiar. It's the usual thing that everyone does in Prolog in their first couple of sessions. Right. It's an all male and child world. So I'm asking for all the grandfather and grandchild relationships, given that, Abe is Homer's father, Homer is Lisa's father, Homer is Bart's father, and Homer is Maggie's father. And then there's the rule for grandfather in there, which, doesn't include women, I guess. I'm not PC. So, when I say that, you get the right answers. It enumerates all the 3 relationships that you care about. So, quickly, I'm going to show you a couple more of these before I move on to the meaty stuff. Where is that? By the way, this is a wiki, also, and so anyone who's interested in this stuff can just open up this web page on their browser without downloading anything and see these projects, try them out, and make their own projects, save them, and so on. So, okay. On this page, what I have, roughly a page of code here. This is logo syntax. And on the left-hand side, you see sort of the BNF-style rules to describe the logo syntax using left recursion and stuff. It's fairly readable. And on the right-hand side, there's some JavaScript code that's being output by the semantic actions. And then, this is the neat part. After I've defined the language, and there's a little bit of runtime support above the grammar, I can redefine translate code to be a function that takes in the code that you tell it to evaluate, and then passes to Smiley, my turtle, the code to evaluate, and doesn't return any useful value. undefined, by the way, I'm returning the undefined string because when JavaScript tries to evaluate the undefined string, it's not going to do much. So if I select all the stuff and tell it to evaluate, quickly this added, my code added dynamically added canvas elements to this page. And then down here, so it's also switched the language that's understood by this browser, by this workspace. So I can teach it to do a spiral, which is code that I actually took from the Wikipedia page on Logo. And then if I tell it to draw a spiral, and I can, it's too quick, I messed up, but I can draw another one. Well, hopefully you don't think I'm cheating, but it actually draws in real time and it looks really cute. So anyway, now I'm going to show you some more interesting examples. First thing I want to show you is that there's a little JavaScript compiler. It's not really a compiler. That's a bit of a misnomer. What this is, in this case, by the way, I have implemented a very nearly complete subset of JavaScript. It's about like maybe 90 or 95% of the language using Ometa. And I have a translator that takes the JavaScript program and outputs some small talk, and it works on top of Squeak. So that's pretty neat to play with, but I don't have time to show that today. And I have a couple other backends for that. But in this case, what I have is a JavaScript parser written in Ometa. That's about 120, 140 lines of code. I don't remember exactly what it is. And then after that, I have a translator that pattern matches on the parse trees that I generate and outputs the JavaScript code again. So it's sort of the identity transformation on JavaScript, which on its own is not very interesting, but the neat thing about it is that once you have something like that, you can easily, because Ometa is object-oriented, you can inherit from these grammars and override certain rules. For instance, if you want to add a new kind of statement, you override the statement rule and add some new construct stuff. So I'm going to skip over that example, but you guys get the idea so far, right? Okay. And of course, Ometa is implemented in itself. Oops. So in a very similar style to that JavaScript translator that I just showed you. So this is the parser for Ometa, and underneath is the code generator, which just translates the parse trees to JavaScript. And I have a little bit of a library that I wrote that's maybe something like 50 lines of code or whatever that supports the semantics of Ometa in JavaScript. And that's the way I bootstrap Ometa on a new platform usually. I just implement a very minimal set of semantics as a library in that host language, and then I do the parsing and code generation in Ometa. But one interesting thing here is that you don't have to do this, very direct two-step process. You can do some more interesting things with it. So, for instance, the Ometa translator is just taking a parse tree and outputting the JavaScript. But my parser is not extremely smart. For instance, if you have nested OR expressions, while you're doing your pattern matching, as you often do, if I use parentheses, I say X or Y or Z, that's going to generate two OR operations, and the OR operation in Ometa has to remember the position that you're at so that it can backtrack properly and so on. And that's sort of wasteful. So one thing that I did that was very straightforward was I implemented an optimization framework for Ometa parse trees in Ometa itself after I had the stuff working. And so what you see on top here is a grammar that pattern matches on a parse tree for Ometa. And by looking at this, you can see how little you have to implement in order to have a language like Ometa. It's very similar to Brian Ford's pegs. You only have OR and Kleene star, Kleene plus. This is assignment, which is used for binding expressions to names. There's a not operation, look ahead, and so on. So it's fairly straightforward. Anyway, this is kind of like a visitor for Ometa parse trees. And on its own, it's not very useful. But then down here, what I'm doing is I'm inheriting this visitor and overriding the and or rules so that when I have nesting, if I have an and that has an and as an argument, I can pull out the parts of that and into the outer and the semantics is going to be the same, except it's going to be more efficient because I only have, to implement that one operation. And when I implemented this, the Ometa.js implementation became, I think, 30% faster, which was pretty neat for very minimal effort. So, anyway, I think... Oh yeah, and the last thing I wanted to show you here before I show the Dan stuff is, so if you end up taking the time to look at this stuff online, I encourage you to look at this project. It's called Meta2, T-O-O, which is a pun on, the Meta 2, which had the Roman numeral 2, that I told you about before. And what this is a language that's very close to Ometa, implemented entirely in this little project. And so, at first, this JavaScript object that you see up here is the library-like object that implements all of the semantics that you need for doing the parsing and pattern matching. And then down here, what I have is the parser for this language written in Ometa. And then I have a couple of examples, with arithmetic expressions and so on. But then, of course, that is not sufficient to do bootstrapping. What you really need to do is once you have the Ometa-like language working, you want to write that, you want to implement that guy in itself, which is what I do down here. And, you can see it's a little bit uglier than Ometa, particularly because the semantic actions have to be, enclosed in these funny characters and so on. But I did that so that I wouldn't have to implement a JavaScript parser as part of this thing, right? So I can just blindly consume the JavaScript and output it, in the translated code. So, anyway, that's the implementation of that, and you can compile the compiler with the original compiler that I wrote with Ometa, and it works. And then the thing that really tests it later on is if you take the version of the compiler that was generated from the code up here by using the Ometa, compiler, if you take that and compile it with itself and replace the thing you're using with that result, and it still works down here, you're good. And that kind of works. So it's a neat little example of bootstrapping, if you want to take a look at that later on. So, I think, one last thing that I want to show here, and take a quick look at this. JavaScript doesn't have multi-line string literals, right? But if you look at this, I'm actually using one right here. It looks very Python-esque. And the reason why I can do that is because, of this translate code thing, my JavaScript doesn't have to be JavaScript, right? I have that intermediate thing, the JavaScript parser and translator that I showed you before, and I can easily inherit from that and add new kinds of things. So that was very straightforward. And the other neat thing about having these languages implemented in Ometa is that there's a thing called foreign rule invocation that allows a grammar to lend its input stream to another grammar temporarily. And it's an alternative to inheritance. For instance, you may have noticed that the language that I'm using in this workspace is not just JavaScript and it's not just Ometa. It's kind of a mashup of these two languages. And if you wanted to implement that with single inheritance, you would have to inherit from one of these translators and then implement the functionality of the other translator, which would be very annoying to have to do. And multiple inheritance is clearly a bad idea. I'm not going to go into that because of all the, complications and so on. And so with foreign rule invocation, I can just have one grammar that doesn't inherit from either if I don't want to, and just says, try parsing my input as an Ometa grammar, and if that doesn't work, try parsing my input as a JavaScript statement or expression or whatever. Sorry. Punchline, yes. Okay, so what you're looking at here is part of my translator for the Nile language that Dan was talking about. So the stuff on top is a grammar that on its own implements the offside rule, indentation as block structure that you see in Python and Haskell and so on. the neat thing about that is that that's modularized away from whatever language that you're implementing. So all the stuff like keeping track of a stack of indentation levels and so on, that can be done in that one grammar. And my Nile parser, which is down here, also written in Nomada, just inherits from that guy and can just say, you know, I want to indent. No, that's identifier. Anyway, there's a bunch of indentation code. Here we go. So I want to tab over here, and then there are these funny Unicode characters that Dan is very fond of, and so on. So this is the parser part of the implementation of Dan's thing, and there's also a type checker and code generator that are written by pattern matching on those data structures that I'm creating on the right-hand side. And so it's a fairly, you know, one of the cool things about Dan's language is that in addition to, you know, types being used for making sure that you don't get things wrong, the types matter a lot for efficient code generation for Nile. And it turned out to be relatively straightforward to keep track of types in these grammars, since, you know, the grammars are kind of like class. A grammar in Nomada is pretty much like a class in an object-oriented language. You can have state associated with running instances of that grammar, and then you can keep the symbol table on there and so on, and do proper type checking. So I think I'm going to stop here. Sorry if I ran a little long, and Hessam is going to take over.
That has to be done also. And in our total code count, we actually count all of our tools. Because certainly the spirit of what Smalltalk was that when kind of forward the last code that we were kind of involved in system so you can set an operating system. So the idea is there is no outside program on this thing. We're just marching through the things that should some of them are easier than others. These, Meta, this particular approach to configuration was a nice route because this has been worked on by a lot of different kinds. So when you take perhaps 10 styles, this style is a style that most people are not familiar with, but it was quite well known in the 60s. It lends itself particularly to this way of doing things with the design. And the PEG stuff that Alex put in there allows left recursion, allows it to be efficient, and allows it to parse the way it says, as opposed to sending the project generator to the end. I'm not sure what the grammar is actually.
And just to clarify, pegs on their own don't support left recursion, but there's a cool trick that you can do with a memo table that's used by Packrat parsers. I wrote a paper about that, if you guys are interested.
I answered a question that hadn't been asked. Any questions about this stuff?
Dan?
You have all of these levels with metaprogramming and so on. How do you make sure that it's actually doing what you think?
Right. So right now I don't have a great answer to that. I tried out, and hopefully it works. But we're hoping that at some point soon we're going to be able to use for instance, the Nile programs that Dan has. I kind of think of them as the meaning of the thing that I care about, and it would be really great to have an automatic way to check the meaning against the. It's true. Okie dokie. So we can discuss it offline. You don't need this to.
This is Hassan's community who was at Intel for a number of years and then is now a graduate student at UCLA. And what he's been doing is working on one of the sort of the next level of difficulty, which is essentially part of what your question goes after. Now, the way I look at it is, even when you're writing in terms of predicates, anybody who has been through oil research knows that values and comparable of decimal theorems that the proofs with that. So we supplied many PhD theses for math students in the sense because it was actually very hard to do a good proof and another research. So having great unit tests, you still don't know the recovery model and so forth. So our theory is that you should be able to specify meaning in a way that is has the smallest amount of ambiguity possible. It could be in terms of concerns or predicates and stuff like that. But you still have to debug it. So our theory of specification language is it doesn't count unless you can run it. Even if it doesn't have any, even if it's not really a functional language, and even if it's not any variable, you still have to find a way to run it. And that's what Hassan was going to say a few words about.
Thanks. Please feel free to leave as we're out of time. I'll be another 10 minutes. I'm Hassam. I work at Viewpoints as well as I'm a student at UCLA. I actually called my father, but he said, "Son, you should be out partying." So part of what we're interested in is, I'm sure you have seen imperative as well as declarative methodologies to do programming. Imperative is how implementations are done, and declarative is, we've seen Prolog language, it's meanings. They're compact. They're very understandable, but we need search in order to execute them, so they're often not practical. Part of what we're interested here to save codes as well as to add understandability to problems is there a way to kind of combine both at the same time, which is not very common today. This is a famous quote that I made recently, that the natural combination of declarative and imperative is missing. Couple of methodologies that we kind of studied in this direction is one is I'm just going to quickly go over it, but basically if you add a layer of logic on top of your languages to support search, basically your heuristic search, you can do imperative programming with a little bit of overhead if you're always willing to add optimizations. So in the presence of multiple methods, if there's an optimization that always tells you based on the state which method is the good method to take. So you always do this check to find out the different alternatives. Then you have this little bit of overhead of checking to do your normal imperative. But when you do have the leverage to do kind of search, you have the option to say, explore possibilities and find the best scenario to do. So this is what this project is all about. Allows you to kind of separate the optimizations and heuristics from the actual implementations, the actions that you see here to satisfy the goals. So it implements a bunch of programs, really small. They're really cute and slow, but they have this nice way that you can add. For example, this chess program that was about 300 lines of code that even included some text ASCII art graphics, where you could just actually add any arbitrary number of heuristics that say, based on the states that you explore, basically heuristics tell you which one is the better one to do. And then these heuristics tell you that, it's better to take a move when you actually capture the opponent's piece than try not to get captured. So adding some numeric values so you can basically reorder the alternatives. But another more serious one was, compilers need to do register allocations, which is you have registers and you have variables in the program. These variables, the compiler needs to decide where they're going to be on the registers. And this happens to be an NP-complete problem. It's a hard problem if you want to do it optimally. And then this is a nice way because, you just allow a high-level goal that kind of this is using methodology in a Smalltalk program that you just express the goal that all variables want to be, assigned, and you then you tell it what actions are taken when you're doing this task, which is usually assigning a particular register with a variable, or deciding to spill or split. And then you define the optimizations on top of this that says, based on whatever state you are, if you have room for the next variable, then take that particular method. If you have otherwise, take the spill method. It just has a layer on top of your normal logic. You can express that in more declarative way. But the problem with heuristic search, as you know, is that if you're implementing your own search, it often becomes interactable. So recent studies that I'm going to show now is more based on Boolean satisfiability, SAT solvers, constraint solving technologies, which are recently been shown that it's much, they scale much better. So our more recent stuff is not based on the search that we come up with ourselves, but based kind of plugging our whatever tool that we have to external tools that are really good at solving problems using SAT solving technologies. As we will see that they have their own problems that they're kind of not very they're not nice to adding user-specific heuristics. So eventually we want some combination of the two ways, the heuristic search and or SAT solving technologies to we think that might answer our problem. So this project is about adding syntactic sugars to programming languages. In this case, I'm showing you examples from an extension of Java language, where we are allowing first-order logic expressions like this, or set comprehension, stuff like this. This is from Alloy language. Actually, it's a object modeling language. So we allow these kind of expressions in the language, but they serve two purposes. One is that we can easily desugar these to low-level syntax of the program. So these are actually runnable. So if this is actually a part of the code of the binary tree, and if I actually instantiate an object and I run it, because it's going to be compiled to a low-level code, it's going to be runnable, even though it's compact. But that's not the only thing that we're interested to save lines of code. We're also interested in having runnable meanings that are actually executable. You see, when we say meanings, we mean high-level expressions like this that says, I want a graph that is acyclic. Then this is the meaning of acyclic, that there's no node that kind of points back to itself, right? And it's nice to be able to, without any implementation, actually be able to execute this. Meaning that not just running in the program, that kind of using some constraint solving technology to actually find a satisfying state for that particular constraint. So that's what I'm saying, executable in terms of we can use some external tool to get to what state that we're happy without actually any implementations. And we're going to use that for two things. One is software reliability. I'm showing you an implementation of a bubble sort in this extension. That's pretty routine. It's a bubble sort routine, but we see that this is in light of program annotations you've seen in a Java modeling language and others, where you just annotate the program with meanings, basically, which says this particular method is accomplishing this expression. This is followed by that ensures clause that says the job of the sort method is that it's going to find some value that's a permutation of the old list, and it's going to be assorted. This is something that we can automatically instrument in the compiled version, so that when methods are done, these constraints these expression is going to be evaluated, and if they happen to be false, that means the method was faulty, method was buggy. Or if they even happen to have some kind of runtime failure, like a division by zero, that is not easily found, we can kind of catch that exception and use these specifications as kind of a fallback, as an alternative that the method didn't work, but we can have an alternative to try accomplish what we want. In this case, we can use we kind of translate this expression into the logic syntax, where we can call an external tool to basically sort this list. So it's a little bit bigger example is this is an implementation of red-black tree that also have annotations for the insert and delete methods. Basically saying on an insert you just have one new node added to the set of nodes, and on a delete you have one less. And basically, assuming they have some implementation that's not reliable, you can just use this the annotations to accomplish what they do. Actually, you can think of this. So I found the implementation typically about 500-600 lines of code or 300 lines of code of Java, because of a lot of corner cases that these balance trees need to satisfy. This, you can think of it as a kind of a minimalistic, runnable implementation, as you will. It's like an interface for the whoever wants to implement it. But the neat thing that this has, that the interfaces don't have, is runnable. So you can actually write what these two methods are going to be in the future. But because you have annotated them, actually we can test them and run them, because we have that underlying reasoning system, so that you actually without the implementation you can test your program interface to move around. So this is the last thing I'm showing, is that you can always intentionally use this fallback system, use of fallback, when you want to do something declaratively. You don't even want to implement something, but you can use the constraint solving technology that kind of embedded in your language to accomplish something that's kind of cumbersome. So in this case, for example, this is a GUI example where this is very simple. A user just puts the dots on the screen. You see these 4 dots are put in screen without a problem. So the job of this particular method, the add dot, is very trivial. It just draws the dot, and this box shows that there's this restriction on this application that says a user should not put 2 dots too close to each other. There's a minimum distance they might have. So if you imagine the normal invocation of this method is very trivial. It just draws it. As far as those violations are not, those specifications are not violated, it's okay. But under a corner case is when actually somebody put a red dot here, and that kind of violated that property. You don't want to implement that. That's a hard thing to do. Potentially a lot of dots needs to be moved around, right? So in that case, you just don't handle it in your program, and we're going to kind of automatically fall back to constraint solving and a SAT solving to basically shift some dots around to satisfy those properties, and that's what's happening here. And you see that box here is saying there's a restriction of how much those dots are allowed to shift by the method. So you see that these two are shifted a little bit to make sure this separation is happening. So basically, I'm showing you the code that does this. This is the entire code that when you're adding a dot, you see that it has this check that it needs to do, that I'm written here also in a high-level syntax of Alloy, the first order logic that have the 2 things that says no 2 dots needs to be too close to each other, and when you do move them, you're not allowed to move them by more than a value. And you see that there's no implementations here, so that when I put that red dot, it kind of automatically figured out the moving. Those are the things that just wanted to show you. So if you have any questions, or for previous.
slower ways of doing things until we get sitting down and we write another optimization. But the idea is that the optimizations actually don't count as real code. They're just optimization, and at any time you should be able to turn off the optimization, and your system is built to run. Okay, so questions of Hassan?
Actually, I was curious, when you have that fallback of the optimization to the specification, when you do handle side effect, say you go through the optimized program and realize that you
So in our prototype, we clone objects, and specifications have to happen to care about the previous state of the objects before the method was run. We actually copy them. So there's the overhead of copying things that you don't trust the method, to not work. And then to have it basically ignore those. Those are the things, of course, those are the things that can be turned out. There's side effects that are harmful that we cannot do anything about.
So also,
those are the things that we don't have a answer.
to refer you to Alex's thesis, the other part of Alex's thesis is the general context mechanism for multi-grain speculative operation called worlds. So you can find that. The basic idea is you would like to have something that is like what are called possible worlds reasoning now, but to be able to use it efficiently at every level of things. You'd like to be able to use it for undo, use it for interface level. You'd like to use it for backtracking. You'd like to use it for this case, and you'd like it to be efficient at each of the levels of training when you use it. So this is part of this idea of modeling time. By actually controlling time by what it means to have local states in various ways. You can have a lot of things that involve the same naming entities, but they're actually in different time zones. Any other questions? So thanks a lot. It was a pleasure to come and share our stuff with you. Thank you.